Have you ever really thought about why a soccer ball grinds to a halt, but a satellite just keeps on going and going and going? Well, today we're unlocking the secrets behind that, and honestly, so much more. We're diving deep into the fundamental rulebook for pretty much everything that moves, Newton's 3 incredible laws.
I mean, really, picture this for a second. You give a soccer ball a good kick, it flies for a bit, and then it just stops. But a satellite? It's been zipping around our planet for years. What gives? Well, the answer is hiding in plain sight, inside 3 simple but unbelievably powerful laws that we're about to unpack together.
All right, first up, we've got law number 1, inertia. Now, I like to call this one the just keep doing what you're doing law. Seriously, you could think of it as the universe's default setting for, well, for everything. Okay, so here's the official textbook definition. An object is going to stay in its current state of motion unless some kind of external force comes along and messes with it. The 2 phrases you really got to know here are state of motion, which is just a fancy way of saying whatever the object is doing, and resultant force, which is basically the grand total of all the pushes and pulls acting on it.
So, what happens when all those forces are perfectly balanced out and that resultant force is 0? Well, 2 things can happen. 1, if an object is just sitting there, it's going to keep just sitting there. Makes sense, right? But, and this is the cool part, if it's already moving, it's just going to keep on moving at the exact same speed in the exact same direction. That, right there, is inertia in a nutshell.
Now, I know that can all sound a little abstract, so to make it super concrete, let's use one single example for this whole explainer. A car.
Imagine you're just cruising down the highway, nice and steady at a constant speed. The car's engine is providing a force pushing you forward, right? But at the same time, air resistance and friction from the road are pushing you backward. When you're at a constant speed, those forces are perfectly balanced. They cancel each other out. And the result? Constant velocity. That's Newton's first law playing out right in front of you.
But what if you want to speed up, or slow down, or, take a turn? Well, for that, you have to break the balance. You need an unbalanced force. And that, my friends, leads us perfectly into law number 2.
So if the first law is all about things staying the same, the second law is where the action is. It's all about change. It's the engine that drives acceleration, and it's all wrapped up in one of the most famous equations in all of science.
And here it is. F equals ma. Force equals mass times acceleration. This little tiny equation is an absolute giant of physics. It's the recipe that tells us exactly how an object's motion is going to change when you push it or pull it.
Okay, super quick rundown of the units so we're all on the same page. Force, that's measured in newtons. Mass is in kilograms, and acceleration is in meters per second squared. Got it? Good. Let's see this thing work. Check this out. A cheetah has a mass of about 22 kilograms, and it can accelerate at an absolutely insane 15 meters per second squared. So, to find the force its muscles need to generate, we just plug those numbers into our formula. 22 times 15, and that gives us a whopping 330 newtons. That is some serious power, all thanks to F equals ma.
Okay, your turn. Time to put on your physicist hat. Using that same exact formula, what's the force needed to accelerate a 15-kilogram gazelle at 10 meters per second squared? Go ahead, do the math. I'll give you a second.
Did you get it? Mass times acceleration, 15 times 10, it's 150 newtons. See? You got this. You're a physicist.
Now, before we get to our final law, we have to take a quick detour to clear up a really common point of confusion. We got to talk about the difference between weight and mass. They sound kind of the same, but in the world of physics, they are totally different things.
So here's the deal. Mass is basically the amount of stuff an object is made of. It's measured in kilograms, and it's constant no matter where you are in the universe. Weight, on the other hand, is a force. It's the force of gravity pulling on all that stuff. So while your mass is always the same, your weight can change. You'd weigh less on the moon, for example.
And get this, the formula for weight looks really familiar, doesn't it? It's weight equals mass times g, where g is just the special name we give to the acceleration caused by gravity. So you see, weight isn't some mysterious property. It's just another force, playing by Newton's second law. Okay, so we've covered the law of staying the same and the law of changing. Now for the grand finale, Newton's third law. This one is all about interaction, and it reveals a fundamental truth about the universe. Forces never, ever act alone. They always come in pairs. Here's the official word. Whenever 2 objects interact, They exert equal and opposite forces on each other. You've probably heard the short and sweet version of this. For every action, there is an equal and opposite reaction.
Let's go back to our car one more time. How does it actually move forward? It's this beautiful dance of action and reaction. The tire grips the road and pushes the road backwards. That's the action. And in response, the road pushes the tire forwards with an equal force. That's the reaction. And that forward push from the road is literally what moves your car.
Or think about something even simpler. When you push a stroller forward, you're not just applying a force to the stroller. At the exact same moment, the stroller is pushing back on you with the exact same amount of force. It's this perfect, balanced interaction every single time.
So there you have it. 3 laws. One for staying put, one for getting a move on, and one for how everything interacts. Now for the real magic. Let's put them all together and see how they paint the complete picture of motion.
Our car's journey tells the whole story. When it's parked, it's pure Law 1, an object at rest. To get going, we need Law 2. We need that unbalanced force from the engine to cause acceleration. Once we're cruising at a constant speed, we're back to Law 1, with all the forces balanced out. And the whole time, from start to finish, Law 3 is at work, with the tires and the road pushing on each other. See, they all work together. And that brings us right back to where we started, our mysterious satellite. So here's a final mind-bender for you to think about. We know the Earth pulls the satellite towards it. But according to Law 3, the satellite must be pulling on the Earth with an equal and opposite force. So, why does the satellite do all the moving? Why doesn't the Earth get yanked around in the sky? The answer? Well, it's hiding in everything we just talked about, in the relationship between force, mass, and acceleration. Thanks for coming along on this deep dive into Newton's amazing laws.